Hi guys, welcome to lesson 21-2, which is about exponential functions. For this lesson, you will find a note sheet that I've posted on Google Classroom. You will want a pen or a pencil and also your calculator nearby. Our learning targets are that we are going to identify and write exponential functions, and we are going to determine the decay factor or the growth factor for those exponential functions. Okay, so let's go ahead and get started. An exponential function is a function of the form f of x equals a times b to the x. So that's going to be super important for you guys. Obviously, it is a and b are constants, so a times b to the x. So x is the exponent. That's why it's called an exponential function. Okay. X is the domain, f of x is the range, so that's still the same as always. X is the domain, y is the range. And then your a value cannot equal 0, because if you multiply something by 0, we know that equals 0. And then your b value has to be greater than 0 and also should not be equal to 1, because 1 to any power, even if you did like 1 to the 17th and that was the exponent, 1 to the 17th is still 1. So that's why it says here that the b value cannot be 1, cannot equal 1. Okay, so this here is an example. If you look at this table, each term, you can see that they are dividing by 2. Oops. So 24 divided by 2 is 12. 12 divided by 2 is 6. 6 divided by 2 is 3. 3 divided by 2 is 1.5 or 1.5. Okay, so what they're doing each time, it says the increase in consecutive x values results from repeatedly adding 1. So that's what's happening with the x values, while the decrease in y values results from repeatedly multiplying by the constant 1/2. So remember that multiplying by 1/2 is the same as dividing by 2. Okay, so to relate it back here in a minute, we'll be talking about whether it would be like whether it would be a geometric or an arithmetic pattern. So this one, because it's multiplying by 1/2, it would be geometric, right? From what we did in the last unit. Okay, so the big thing to know here is that we're going to be focusing on your base b. So this here is your b, it's your base. And it says here, if the base is between 0 and 1, then the exponential function represents an exponential, and we're going to call that decay. Let's see if I can fit this all in here. So exponential decay is the word we're looking for. And then if your base is greater than 1, that's going to be your exponential function then represents an exponential growth. Okay, so this makes sense. A number greater than 1 is going to be growth. A number between 0 and 1, so a fraction like 1/2, let's say, that would be decay. Okay, so something like y equals 1/2 to the x, like we just saw up there, that is going to be decay, but something like y equals 2 to the x, that is going to be growth, because that b value, the one that has the exponent with it, is going to be it's going to be a whole number greater than 1. Okay. All right, awesome. So make sure you have that jotted down. And let's go ahead and identify whether these would be growth or decay. So again, the function is f of x equals a times b to the x. And you really want to focus on this b to the x. So whatever has the exponent, the x attached to it, that's what you're focusing on. So in this one here, we have 7 times 3 to the x. So 3 is greater than 1. So that would mean that this is exponential growth. Okay. In this next one, f of x equals 5 times 1/4 to the x. Again, you're just focusing on that. So 1/4 is less than 1, but greater than 0. So remember, if it's between 0 and 1, that is going to be decay. Okay, so then you guys think for a second here, part C, if it is f of x equals 1/4 times 2/3 to the x, is that going to be exponential growth or decay? Go ahead and answer here. So hopefully you said that 2/3 is less than 1 but greater than 0. So this one would also be exponential, decay. Awesome. All right, moving right along. So in these next couple, we are basically going to be looking at some patterns here. So I would jot down the following information because we are going to be referring back to somewhat what we talked about in our last little section that we quizzed on. So what we're going to be doing is looking at these tables and determining if it is a linear function, an exponential function, or neither. If it is exponential, we're going to determine whether we think it's exponential growth or decay. But first, linear is most similar to arithmetic sequences, meaning we're going to be looking for a pattern that has a common difference that is adding or subtracting each time by a constant, okay? Whereas exponential is more like geometric, meaning it should have a common ratio or a constant that we are multiplying by each time. Okay, so I would definitely make sure you have this written down somewhere. That is super important to kind of relate it back to our last unit. Okay, so looking at part A, again, our x values just go 0, 1, 2, 3, 4. So those are just going up by 1 each time. But what is the pattern of our y values? What's happening here? Okay. So think about that. And how do we get from 1 to 3? Well, you're either adding 2 or you're multiplying by 3. So then think, how do we get from 3 to 9? Oh, well, here you're going to be multiplying by 3 again. So that looks like it's the pattern. Multiply by 3, multiply by 3, and then 9 to 27. Oh, yeah, that's multiplying by 3. 27 to 81. Yeah, that's multiplying by 3. So this one would be an example of an exponential function. And that is, again, because we were multiplying exponential, same as when we were talking about geometric. Okay, so now we know it's exponential, but again, we need to determine if it's growth or decay. But what we were multiplying, so what our b value would be is 3. And the numbers are growing, so this would be an example of exponential growth. Okay. Cool. Then let's take a look at part B. These are, again, the x values just going up by 1 each time. But what's happening with these b values? So from 4 to 8, again, that's either adding 4 or multiplying by 2. But then from 8 to 14, that is actually adding 6. So it's not adding. And it's also not multiplying by 2. So this one would be an example of a neither type of problem. Okay, because we are not adding by a constant, nor are we multiplying by a constant each time. So this is a neither. Okay. And if you wanted to, you could write that in. So like add 4, add 6. And so that's not by a constant. Multiply by 2 and then 8. You can't get 8 times 2 would be 16, so that doesn't work. So that is a neither example. Okay. And then last one, again, our x values 0, 1, 2, 3, 4, so we know we're good to go there. But what might be happening here? So you're trying to see the pattern. So from 24 to 18. Okay, so it doesn't look like we are dividing by anything. It looks like 24 to 18, you're subtracting 6. 18 to 12, also subtracting 6. Also subtracting 6 here. And then 6 to 0, also subtracting 6. So because it is a subtracting, this one's going to be linear. And that's all we have to say here. We don't have to say whether it's exponential growth or decay, but this one, if it were linear, it is decreasing, we could say. All right. So that is really it for being able to look at a table and determine what the pattern is, determine whether it is exponential or linear or neither of those two. Okay. And last part here is that we might need to fill in a table. So these say complete the table for each item, then write the exponential function. So given that the function has an exponential decay factor of 0.8, we are going to have to write the function. So first of all, in order to write the function, we are going to write it as f of x. And then because it gave us the decay factor, that's actually your A. I'm sorry, your B. My mistake. And then what we're going to do is just take whatever that first term is and multiply it by that 0.8. So 64 times 0.8, this is where you'll need your calculator, is 51.2. And then you would just continue to multiply that term by 0.8. So you can go ahead and continue doing that. So 51.2 times 0.8. You should be getting 40.96. Then times 0.8, you should be getting 32.768. And then times 0.8, you should be getting 26.2144. Okay, and you could keep going with this, but it's just asking for these terms here. Okay, and then the next part says complete the table and then write the exponential function. Okay, so we're going to go ahead and do that now. And again, I already kind of told you guys that the b value is given to us. That's the exponential growth or decay factor. Okay, so you know that piece. And then your a value just comes from whatever your first term is. So that's your initial term, which would be here, so 64. So your final exponential function would look like 64 times 0.8 to the x. Okay, so if you want to kind of jot yourself that note, so remember we said this is our function. So if you want to tell yourself a is the initial term and b is the exponential growth or decay factor, that might be helpful to have written down. Okay, very important there. All right, so then let's go ahead and just finish up this next one. So right away we know, okay, again, we can write it as f of x equals, and right away we know kind of what our initial term is here. So at 0, the first term is 4. And then we also know it's going to be a growth factor, so my b value is greater than 1. It's 2.3. And so now let's just go ahead and take 4 and multiply it by 2.3. And you guys can go ahead and do this in your calculator as well. Okay, so we have 4 times 2.3 is 9.2. Times 2.3 is 21.16. Times 2.3 is 48.668. And then times 2.3 is 111.936, 4. And again, this would be your equation here or your function, because this is your initial term and this is your growth factor. Okay. And the numbers are getting larger, so we also know that it is exponential growth. All right, awesome, guys. That's it for today. We'll do some practice in class, so let me know if you have any questions. Have a good one. Bye.